So in this video, we're gonna start a new chapter number 6, which is chemical reaction, and we're gonna talk about the energy, the rate of the chemical reaction, and the equilibrium of the chemical reaction. So the topic that we're gonna cover in this chapter are energy and the chemical reaction, how energy are related during a chemical reaction, and then the second one is the rate of the chemical reaction, how fast the chemical reaction goes or how slow it normally goes, and the third one is the chemical equilibrium. What is meant by the chemical equilibrium in chemical reaction? So now let's start with our first topic, which is energy and chemical reaction. But before we go further into the slide, we'll talk a little bit about energy. What is energy? As we already talked about from the previous chapter, energy is an capacity to do a work. Or as an ability to do a work, right? So for example, whenever you throw a ball, you need some energy, right, to do that work. Or whenever you are riding a bicycle, you are doing some kind of work and you need energy. So all this work need energy, right? So now let's talk about on the next slide what are the unit that we normally use to measure this energy, because units are important, and then we're gonna talk about what are the different kind of unit that we normally measure energy in. Now let's talk about the units of energy. So energy can be measured using two different units. The first one is calorie, the second one is joule, right? So let's talk about these units individually and then figure it out what's the definition of both of them. The first one is calorie. How we can define the calorie? We can define it the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So that means you need to know how much energy you needed to increase the temperature of every 1 gram of water by a 1 degree Celsius. Right, so this is how we define it. The second one is a joule. Joule is the amount of energy required to lift 1 kg by 10 centimeter. And how these two units are connected to each other, this is connected by this equivalency, which is 1 calorie is equal to 4.184 joules. So if you need to interconvert like one unit into a different unit, you can use this equivalency and make use of a conversion factor, and you can convert easily. And if you can see from this equivalency too, a calorie is a bigger in value compared to a joule, because calorie is 4.184 times joule. Now let's talk about the third one, which is called nutrition calorie. So how we define nutrition calorie? For example, whenever we eat food, right, for example protein, carbohydrate, or a fat, we get energy from these food, right? From whenever we eat, body convert this food into energy, right, so that we can do some work. So how we can define nutrition calorie? Nutrition calorie is the amount of stored energy present in the food, right? And then we usually measure that energy in the food in nutrition calorie. And nutrition calorie, if you can see over here with a capital letter C, is equal to 1 kilocalorie. So I can say 1 calorie with a capital letter C equal to 1 kilocalorie, right? And then I can say what is kilo? Kilo is 10 to the power 3, 1,000 times calorie, right? But the important thing over here, make sure you know this difference. A nutrition calorie start with a capital letter C, and then the simple calorie with a small letter c. So make sure you know this difference. So whenever I write a capital letter C calorie, that means is equal to 1,000 small calorie. So now we already talk about all the three units that we normally use to measure the energy: calorie, nutrition calorie, and joule. But these calorie with a small letter C and joule, both are a small unit, right, in measurement. So most of the time whenever we measure energy in calorie and joule, we usually use a different unit which we call as 1 kilojoules. So if I write 1 kilojoules, that's equal to 1,000 joule, because K is a kilo. Similarly, if we have 1 kilocalorie with a small c, that means this is 1,000 calorie. So you can use also these equivalency to convert one unit into a different unit, right? So let's get to the next slide and then try to solve some of the problem based on this concept that we just learned on this slide. Now let's try to do a couple of problems based on the concept that we learned on the previous slide. So the problem says convert these into calories, right? So the first problem is 5.79 kilocalories, how many calorie? So we already know this equivalency, 1 kilocalorie is equal to 10 is 1,000 small calorie, right? And we can use this equivalency to make a conversion factor. So how we can solve this one? So I can say it's 5.79 kilocalorie, and we need calorie in our answer, so this number has to be on the top, small c, and then 1 kilocalorie. So kilocalorie is gonna cancel it out, and then you will end up with 5.79 times 10 is power 3 small calorie. And if you want to open it, right, you don't want to use a scientific notation, you can also write into a standard number, which come out to be 5790 calorie. So this is how you can convert a kilocalorie into a calorie. Let's try do the second problem over here that says if you have 48.8 joules, how many calorie you have in there. So again, we already know the equivalency, how calorie and joules are connected. We know 1 calorie is 4.184 joule, and we can use this equivalency to make a conversion factor, right? So we're gonna use 48.8 joule times, and I can make one conversion factor. We need calorie, so 1 calorie on the top and 4.184 joules on the bottom. Then joules will get cancel it out, and then when you divide 48.8 by 4.184, you're gonna get around 11.7 joules, right? And you need 3 sig fig number because 48.8 has 3, that's why you have 3 sig fig number over here. So we can say if we have this is calorie, not joule. See, so we can say if we have 48.8 joules, that means I have 11.7 calorie, so they are equal, right? So this is how you can convert different unit within each other. Let's try to do one more problem where you convert one unit of energy into a second unit. So for example, if we have 421 kilojoules of energy, how many kilocalorie you have in there? So you have to just solve this problem. So we already know that 1 calorie is equal to 4.184 joule, but if you can see, for the given unit is given in kilojoules, and the unit that we required is in kilocalorie. So I can convert this equivalency something like this: 1 kilocalorie is equal to 4.184 kilojoules, right? Because we are putting just 1 kilo on both sides, so it doesn't change the value for this equivalency, right? So I can make a one conversion factor using this equivalency that we just did. So I can say 421 kilojoules, I can write 4.184 kilojoules on the bottom, and can write 1 kilocalorie on the top. Kilojoules will get cancel it out, and then when you solve it, you're gonna get around 100.6 kilocalorie, and you need 3 sig fig numbers, so I can round it off this thing to 101 kilocalorie. So I can say if I have 421 kilojoules, that means I have 101 kilocalorie. So this is how you can use the concept to convert one unit into a second unit. So this is another example beside the two that we did on the previous slide. So now let's talk about the exothermic and endothermic reaction. But before we go on to these topics, let's talk about what are the different kind of energy that we know from the previous chapter. So energy can be of two types. One of them is kinetic energy. Second one is potential energy. So matter can have these kind of energy. So what is kinetic energy? Kinetic energy is the energy associated with the motion, right? And then what is potential energy? Potential energy is the energy associated with the position of the substance, right? For example, if you put a ball on the top of the hill, that means that ball has some kind of potential energy because this is up from the surface of the earth, right? Similarly, if we have any kind of molecule, for example, let's say water, so the bonds that we have in water also have some kind of potential energy. So that means whenever you break this bond, you release some energy because the energy is stored in the form of potential energy within these bonds, right? So let's say if you have any reaction going on, let's say A goes to B, right, in any random reaction. So A is your reactant, right? B is your product. So whenever the reaction goes from reactant to product, that means there's some kind of change in the energy is happening, right? So just remember this thing, the reaction will always goes from high potential energy to a low potential energy. What does it mean? So if the reaction is going from A to B, that means A has high potential energy and B has low potential energy, right? So low potential energy means the molecule is stable on the product side, because every molecule wants to be stable. They don't want high energy in them. So that's why the reaction always follow from high potential energy means unstable. So that means A is going to convert into B. A is unstable, that's why it's forming a molecule B in the product which has low potential energy and which is stable. But the question is where that rest of the energy goes. So if A has high potential energy and B has low potential energy, and then we already know the energy cannot be created nor destroyed. This is the first law of thermodynamics. You cannot create the energy, you cannot destroy the energy, and energy is conserved. So what does it mean? Where does the rest of the energy goes that we had in molecule A? Because molecule B has less energy, so that means some of the energy is dissipated or goes into the environment in the form of heat. Right? So if the energy is going in the form of a heat into the environment, that means the environment is getting hotter. So this kind of energy or this kind of reaction that release the energy to the environment so that it can get stable, we call that kind of energy as exothermic reaction. Exo means outside. That means the rest and the extra amount of energy that molecule E had is going to the environment in the form of heat. So it's exothermic reaction. Similarly, for endothermic reaction, what is meant by endo? Endo means inside. Whenever the energy being absorbed by the reactant or by the reaction, we call that kind of reaction as endothermic reaction. So remember, these are the two type of important reaction in a chemical reaction. So make sure you know the difference. So let me tell you one more time. Exothermic is that kind of reaction where where the chemical reaction, when convert from reactant to product, the extra energy is going into the environment in the form of heat. Endothermic reaction are those chemical reaction where the reaction or where you're putting more energy to the reactant side. They're absorbing energy. So that's why those are called as endothermic reaction. So let's go to the next slide, and then we can see that we can compare both type of reaction, which is endo and exothermic reaction, and then compare how they are different with each other. So now let's try to compare between the exothermic reaction and endothermic reaction, how they are different. So the first thing that you can use to differentiate them is the heat. So in exothermic reaction, heat is getting released into the environment, right? That's why the term is exo. For endothermic, heat is getting absorbed by the reaction. That's why the term is endo, right? And thermic means energy, right? Okay, so in exothermic reaction, if the heat is getting released into the environment, that means the surrounding is getting warmer, because surrounding is getting the extra heat that the reaction had, right? For endothermic reaction, the surrounding is getting cooler, because if the reaction is absorbing the heat, from where is getting the heat is from the surrounding. So if it's taking the heat from the surrounding, it will cooler down the surrounding temperature, right? And the third, which is important for both type of reaction, let's talk about the exothermic. Reactant have higher potential energy than the product, and it makes sense. That's why the reaction is exothermic. For example, let me explain one more time. If you're going from A to B, if A has high potential energy, right, and then I already told you on the previous slide, reaction always goes from higher potential energy to a lower potential energy, because less the energy the molecule has, more stable the molecule is. So if reaction goes from A to B, that means B has low potential energy, and then we already know the energy is conserved, so the rest of the energy is getting into the environment in the form of heat. So what we can learn over here, in an exothermic reaction, the energy or the potential energy of the reactant is always higher compared to the potential energy of the product. This is your product, right? Same thing for the endothermic reaction. It says reactant have lower potential energy than the product. What does it mean? If the again same reaction, A goes to B, and this is an endothermic reaction, so what does it mean? You are providing an extra heat to the reaction. You're adding up a heat to a molecule that already has some kind of potential energy in there, right? So molecule A has some potential energy, and then you provided some heat energy from outside that was not belongs to reactant A. When A goes to a B, what's happening? So you are getting two kind of energy together, potential energy plus heat energy, right? So that means the energy of the product B in this case is higher compared to the reactant energy, right? So remember, so make sure you know the difference between the exothermic and endothermic reaction, how you can differentiate, because this is important. So if I ask you about the exothermic reaction, you can say always the reactant has higher potential energy than the product, whereas an endothermic reaction, reactant has lower potential energy if we compare with the product. So now let's talk about a new term which is called as bond energy. As the name is already telling you, is the energy of the bond, right? So before we explain what is bond energy, let me tell you about this thing. So let's say whenever the reaction is happening, for example, if this is the reaction, combustion of any hydrocarbon is giving you a product, let's say carbon dioxide and water. So what's happening in this chemical reaction? So we can say that in this chemical reaction, the reactant, which is methane and oxygen, reacting together and converting into a product which is carbon dioxide and water. But what's actually happening in this reaction? So this is the methane molecule with a 4 bond with hydrogen, and let's say this is an oxygen with a bond, right? So if you can see in the product side, the carbon is attached now with the oxygen, but it was not before the reaction in the reactant side, right? Carbon attached with the hydrogen. So how did this reaction happen? So before it can convert into a product side, the bonds that carbon is making with the hydrogen need to break, right? And then that means for any chemical reaction that's going from reactant to the product side, the bond, there are two kind of reaction is happening, or two kind of processes happening. First, the bonds of the molecule on the reactant side is getting broken down, and then in the product side a new bond is forming, right, for carbon dioxide. So in any chemical reaction, reactant, there is always a breaking of the bond. On the product side, you'll always form a new bond, right? Now the question is how you can break a bond. So to break anything, you need energy, right? So to break a bond, you need energy. That means a breaking of bond is as an endothermic reaction, because you are providing energy to the bond to break them apart, right? And similarly on the product side, you are making a new bond, right, so that you can make a new molecule. So making a bond is an exothermic reaction. So remember this thing, whenever you make a new bond between the two molecules, you are releasing energy to the environment, right? So this is the difference between the bonds on the reactant side and the bond that you're gonna form new on the product side, right? So how we can define the bond energy is the amount of energy required to break 1 mole of a given type of a bond, right? So how much energy you require to break a 1 mole of any molecule, or 1 mole of any given type of a bond in a molecule in gas phase. We call that kind of energy as bond energy. So now let's get to the next slide and see what are the average bond energy of some of the bonds, right? So this table that you can see over here, this normally tells you about the average bond energy of some of the bonds, right? For example, if you have to break a bond between carbon and hydrogen, you need to provide at least 414 kilojoules of energy. If you need to break a bond between oxygen and hydrogen, you need 464, and then same goes off within carbon and carbon double bond, right? And if you can compare the bond energy of these different type of bond that we just discussed, we can see to break a double bond you need more energy, right? Because you have two bonds within two atoms, right, compared to all the single bond that you have on the top. So that means higher the number of bond between two atoms, you need more energy to break that kind of bond. Now let's talk about some of the trends in bond energy. So the trend says higher bond energy is equal to the stronger bond with lower potential energy. What does it mean? That means that if a bond, let's say for example carbon and hydrogen, right, if you need more energy, if the bond energy for this bond between carbon and hydrogen are the highest, that means the bonds are stronger. That's why you need more energy to break that bond, right? And the second thing, it says it has lower potential energy. So just remember this thing, if any bond, particular type of bond has higher bond energy, that means that bond is stronger and has lower potential energy. That means that bond is stable. So stronger the bond, stable is the bond, right? Second thing is the compound with weaker bond are more reactive than the one with the stronger bond. What does it mean? It means if you have any two bond, one of the bond is weaker compared to the second bond, so that means the first bond that is weaker need less amount of energy to break it apart, right? Compared to the second bond that is stronger, you need more energy, right? So it's easy to break a weaker bond compared to the strong bond. That means that bond can be easily broken down, and then those atom that's making those bond can form a new bond with any other molecule, right? So that means those atoms are more reactive. The third one is triple bonds are stronger compared to the double bond. If you have any bond, let's say A and B, you have a double bond and you have a triple bond between A and B, so you need more energy to break these three bonds compared to the energy that you require to break these two bonds, right? Double bond. So remember this thing, if you have a multiple bond between the same two atoms, you need more energy to break those multiple bonds compared to the single bond that we had within the same two atoms, right? Now let's talk about a special term called heat of reaction, represented by this symbol delta H or triangle H reaction. And how we can define the heat of a reaction for any chemical reaction is the amount of heat energy released or absorbed during that particular chemical reaction, right? So let's say if you have any chemical reaction going on, let's say it goes from reactant to product. So what's the net amount of energy being released or absorbed during that chemical reaction? We call that term as, that amount of energy as heat of reaction. And how we can calculate this heat of a reaction from a chemical reaction? So we can calculate by summing down all the bond energy of the bond that is being broken during the reaction on the reactant side, and then subtract that with the sum of the bond energy of new bond form on the product side. For example, let's take this reaction again. CH4O2 gives you carbon dioxide and water. So what's happening in this chemical reaction? You have CH4. How many bonds you have in CH4? You have 4 bonds, CH, H and H. Oxygen has, let's say, 2 bonds, 1 single bond. Then on the product side, you have how many bonds you are forming? You are forming 2 new bonds, right? And for water, you are making 2 new bonds. So what's happening in here? So let's assume how much energy you require to break these 4 bonds from the methane. Let's assume this is 20 joules of energy. And how much energy you need to break this single bond between oxygen and oxygen? Let's assume this is 5 joules of energy, right? So this is an endothermic, you are providing the energy, so that's why 20 joules and 5 joules. So how much total amount of energy you require to break everything on the reactant side? So add them up, so it's come out to be 25 joules, right? Let's talk about, so this is the energy that you provided to the reactant, right? So let's talk about the energy that is being released on the product side. So that means you are making couple of new bonds, right? So you're making a bond between carbon and oxygen that was not on the reactant side, right? So, and if you remember, forming a new bond on the product side always release energy. Whenever you make a new bond between 2 new atoms, you always release energy. So that's let's assume you release, when you make these 2 bonds between carbon and oxygen, let's assume you release 20 joules of energy, right? So you're releasing into the atmosphere. And then to make a 2 bond between water, oxygen and hydrogen, let's assume you release 10 joules of energy to the environment, right? So let's assume it is 3 joules, right? So how much energy total on the reactant side, on the product side? 20 plus 3, 23 joules, right? So you started with 25 joules, whatever the bond that you need to break, you provided 25 joules, and to make a new bond you release 23 joules. So how much energy is getting absorbed during this reaction? So that means you started with sum of the bond energy, bond broken 25, and minus sum of the bond energy of bond form 23. So that means it's a 2 joules. So that means this reaction is an endothermic reaction, because whatever the energy that you had in the reactant side, you have less energy being released on the product side. So that means 2 energies of joules of energy getting absorbed. So this is an endothermic reaction, right? Because delta H is more than 0. So that means reaction is endothermic. But if we would change the scenario, instead of 3 joules on the water, let's assume if we release 13 joules now, 1 3, right? So what should be the number then? Then you will have 25 minus 13, because we assume now instead of 3 we release 13 joules. So what's the total over here? 20 plus 13 is 33 on the product side, right? And it's gonna be come out to be negative 8. And if the delta H is negative, less than 0, that means the reaction is exothermic. So this is how you can compare the delta H of the reaction, by comparing the bond dissociation energy or bond energy of the reactant and product, right? So just remember, if delta H is less than 0, exothermic, more than 0, endothermic. So now let's talk about a little bit more about the delta H, which is heat of a reaction. So we learned on the previous slide, if delta H is less than 0, delta H of the reaction is less than 0, that means that chemical reaction is an exothermic reaction. That means the heat energy is getting released into the environment. If delta H of the reaction is more than 0, that means that reaction is an endothermic reaction. Endothermic reaction, right? So let's try to understand what is that means actually. Delta H is less than 0 or more than 0. So if delta H is less than 0, or if the reaction is exothermic, that means more energy is released in forming a bond. Let's say if the reaction is A goes to B for an exothermic reaction, and delta H is less than 0, that means more energy is released in forming a bond on the product side compared to that is needed to break the bond on the reactant side. Because what we know from the previous slide, delta H, how you can get the bond energy of the reactant minus the bond energy in product. That's how you normally calculate delta H. So if the delta H is less than 0, that means more energy is released into the environment, forming a new bond compared to that is required to break the bond on the reactant side, right? So you are losing more energy that you had in before in the reactant side. So that's why the delta H is negative. For endothermic reaction, more energy is required to break the bond. You need more energy to break this bond, the bond between the molecule in the reactant side, compared to the energy being released forming a bond on the product side. So that means you are gaining something. You are not losing energy in endothermic reaction to the environment. So whatever the extra amount of energy that you had is within the molecule by itself. It's not releasing, right? And then one more thing that is important. So the more the energy is released in forming a new bond, right? So the bond will be stronger, right? So let's say, for example, if you make a new bond between C and D, this is a new bond formed, right? And then let's assume you have another product which is E and F. You make a new bond between E and F. So how much energy you getting released by forming a bond between C and D? Let's assume this is 5 joules. And forming a new bond between any molecule, let's say E and F, if you release 7 joules of energy. So which bond is stronger? So the bond between E and F are stronger. So remember, the amount of energy released by forming a new bond is equal to the same kind of energy that you require to break a bond if you need to break a bond between E and F anytime. Right? So let me tell you another way. Let's talk about then C and D. If making a new bond between C and D release 5 joules of energy, because you're making a new bond, that's why you are releasing the energy, right? So now the bond is already formed, and now you need to break that bond. So how much energy you need to to give to this bond to break it apart. Is the same kind of energy that is released while making a new bond, right? So that means you need 5 joules of energy to break this bond again, if you need to break it again. Same thing, the bond between E and F, how much energy you need to break this bond once get formed. Same thing that it release while forming it, right? 7 joules of energy. So bond E and F need more energy to break it. That means the bond is more stronger between E and F compared to C and D, right? So this is a concept that you need to know about this exothermic and endothermic reaction. Now let's try to talk about the energy diagram, right? And then what is energy diagram? Energy diagram is normally shows you the energy changes in a chemical reaction. So what does it mean? Let's say if you have any chemical reaction going on, A goes to B, then how much amount of energy being absorbed or released? How would I know? Then we can show these kind of energy released or absorbed in the form of a diagram or a graph, which we call as energy diagram, right? So if you can see on the left hand side, the y-axis normally denote the energy, and then x-axis normally show you the progression of the chemical reaction, right? So let's try to understand what this graph normally tells you. Let's start with a reactant, right? Let's say this is your reactant. I'm saying this is an A because I use an example reactant as an A, right? So if there's a reactant, and then if the graph goes something like this, and then after the reaction is done, you get a product, right, which is B, right? Based on my chemical reaction, A goes to B. So what's happening over here, if you can see carefully, before the reaction, reactant has this kind of energy, right? But after the reaction is done, the energy on the product side is now this. So what's happened during this reaction? You lose some energy, or the reaction loses some energy. Why? Because the energy of the reactant is higher compared to the energy of the product. So what is this difference in energy? So if you can tell me whether this is an endothermic or exothermic reaction, because the energy of the product is lower, that means the rest of the energy that we had in the reactant is getting converted into heat and goes into the environment. So that means this is an exothermic reaction, because you're releasing energy to the environment, because you don't have that kind of energy that we have in the reactant now in the product, right? And what is this exothermic? What is the difference between these two reactant energy between reactant and product? We call that term as delta H, right? This is the difference in energy, and we know this delta H is less than 0, right? Because you're losing energy. So that's why this reaction is exothermic reaction. Let's go to try to understand for the endothermic reaction. Let's say you start with a reactant now. One more time, let's say this is A, product is B. Now if the reaction is going, the graph will get you will get something like this. And then what's happening over here, if you can see, the energy that you started with the reactant is over here, and after the reaction is done, the energy of the product is higher over here. So that means you gain some energy during the reaction, right? So product has more energy compared to the reactant, so that means some energy is getting absorbed. That's why the product has more energy. That's why we call this kind of graph as belongs to an endothermic reaction graph, right? And how much energy is getting or normally got absorbed is the difference between the energy of the B product side and energy of the reactant side. So this is the extra amount of energy that get absorbed, right? And we call this as a delta H, because delta H is what? The heat of a reaction, how much energy is getting absorbed or released during the reaction. So this is the difference we call as delta H, and this is more than 0, because you're gaining energy. So this is why this reaction is an endothermic reaction. So the important thing from this energy diagram is you will be able to understand, or if you see any kind of graph, you should be able to tell whether it's an endothermic or the exothermic reaction, and depending on whether it's endo or exothermic reaction, you should be able to figure it out what is delta H for that reaction. And how are you going to determine the delta H of the reaction is by getting the difference between the reactant and product side, right? So we can say how we can get the delta H by a formula we can see on the next slide, so that you can get the formula, and then but it's basically the same thing that we just discussed on this slide, how to get delta H. But let's go to the next slide and try to understand what's the formula, how you're going to get delta H from the energy. So on the previous slide we just learned about how to get the delta H from the energy diagram, but the formula is over here. So delta H of any reaction is always energy of the product, how much energy you have on the product side, and you have to subtract from the energy of the reactant. So product minus reactant always. So if this number come out to be negative, let's say if delta H of the reaction come out to be less than 0, that means that reaction is exothermic reaction, because you lose some energy to the environment, and that means product has lower energy compared to the reactant, because energy cannot be created nor destroyed. So the product has less energy compared to compared to the reactant, that the energy that reactant had, right? If delta H, after using the number energy of the product and energy of the reactant, if delta H of the reaction came out to be more than 0, that means you have more energy. That reaction is an endothermic reaction because you absorb some energy. That's why the delta is more than 0. So that means where does this extra amount of energy goes? Into the product side. So product has more energy compared to the reactant that we started with, right? So make sure you remember these kind of thing. This is important to understand the concept of this endo and exothermic reaction. Let's try to do some of the problem based on this concept that we just learned, and then try to figure it out and apply the concept. Let's go to the next slide. So let's try to understand the concept, right, of the problem, and then apply the concept. So this is the chemical reaction going on, right? One of the hydrocarbon C3H8 react with oxygen in a combustion reaction. The C3H8 is a propane and giving you two products, CO2 and water. And then if you can see, you have one more plus sign. That means you're also getting some energy, right? Releasing energy to the environment, because this energy is on the product side. So that means it's an exothermic reaction, right? And then if we calculate how much energy is getting released, or what's the difference between the reactant energy and the product energy, the difference is the amount of energy that is getting released into the environment. Experimentally it's come out to be negative 2010 kilojoules per mole. And how would I know? By comparing this delta H value, whether the reaction is an exothermic or endothermic, by looking this negative sign. So this negative sign means delta H is less than 0, is an exothermic reaction, right? Product has less energy compared to reactant. So this is how you can apply the concept. Let's try to do another example on the next slide. So this is an example of decomposition of aluminum oxide. So aluminum oxide, when decomposed with the help of energy, now you can see the plus sign is on the reactant side. That means you are providing an extra energy to the reactant from outside. So the reactant is getting energy, right? Is absorbing the energy and then converting into aluminum and oxygen, right? So heat is required for this reaction to continue or to carry on. So heat is absorbed, that means the reaction is endothermic reaction on the top. And then if you have to calculate the number, delta H come out to be plus 1676 kilojoule per mole. That means, how would I know? The plus sign means the energy is getting absorbed. This is an endothermic reaction because delta H is more than 0, right? So this is how you can apply the concept. Let's try to do some more problem on the next slide. So now we have to tell whether the two reaction that is given over here is an endothermic or exothermic reaction, right? So the first reaction is S2S, when decomposed, gives you S2 and S8, right? And then heat is getting absorbed. The information is already given or provided to you. So heat is getting absorbed. This is an endothermic reaction. Endothermic. And if you see for the second reaction, carbon dioxide decomposed to carbon monoxide and oxygen, and the delta H values is given, right? For this time the number is plus 566. So the time I see positive sign, positive means energy is getting absorbed. So that means this is also an endothermic reaction. So this is how you can apply the concept again, right? Whether the information is given, heat is absorbed, or with the number is given, you can apply based on the negative and positive sign for the delta H value. So now we're going to talk about the calorimeter on this slide. What is calorimeter and how we can use this instrument to figure it out the delta H of the reaction, right? How much energy is getting released during that particular chemical reaction. So let's figure out what is calorimeter first. So calorimeter, as I already told you, is the instrument to figure out the delta H of the reaction. It is made up of a two compartment, the innermost compartment, the smaller compartment, the outermost compartment, right? So the outermost compartment, you have a water, right, or any liquid, and in the inside of the compartment you put some like food sample or any kind of food that you need to figure it out how much energy that food can give out, right, and how much energy you can get from there. So you put the food sample on the inner chamber, right, and you ignite the food, right, through an electric spark. And then if the food is already ignited, what's going to happen? The temperature of the inner compartment is getting increased. And if the temperature of the inner compartment is getting increased, it will transfer the energy or the heat to the outside water, right? So the more energy is getting released from the food, the more hotter the outside water will get, right? And then you already have the temperature already put, and then you can record how much temperature is getting increased before or after you burn the food sample, right? So the amount of heat energy released, like I told you, is transferred to the water on the outermost compartment, and the change in the temperature is measured. So what was the temperature before you ignite the food, and what's the temperature of the water after all the food sample already burned, right? And every energy that it had, it already transferred to the water. So we can get delta H of the reaction, the heat of a reaction, from the change in temperature, right? So this is how we can use a calorimeter to figure out delta H of the reaction based on how much temperature increased by releasing the energy from the food sample, right? So a calorimeter, we can say, is a device that normally used to measure the heat of the reaction for a combustion reaction, right? And it also can be used to measure the caloric content of different sample of food, right? How much energy that different sample of the food can provide it to you. So this is how we normally use a calorimeter. So as we know that the food sample that we normally eat also provide energy to our body, right, or to the cells that our body is made up of. So how would I know how much energy our body is getting if I eat certain amount of the food sample, right? Certain amount, right? For example, some grams. So our body also do some kind of metabolism, right? So they break down the food sample that we eat and then provide then the energy that being released by after breaking down the food particle is getting absorbed by the cell, and then that energy being used to do some action, right, or to some work by the body. So metabolism of a particular food always release same amount of energy as burning the food in the calorimeter. So if we can do the experiment in the calorimeter, let's assume if we have a chip, a small piece of a potato chip, and then if I ignite that chip in the calorimeter, so if I can calculate how much energy that one particular piece of a potato chip can provide or getting release in the calorimeter is the same kind of energy that the same food sample will provide during our metabolism in our body, right? So by calorimeter we can predict how much energy you're going to get from that particular food sample, right? And then why the food sample normally provide you some kind of energy? Because food sample or food biomolecule always have higher potential energy, so they always have to go to a lower potential energy by releasing energy, right? And that energy is being used by our body, right? So calorimeter is a good instrument that we can figure it out how much energy that each particular food sample can provide to our body. So now let's try to figure out this table. So several tests have been done on different type of food sample or biomolecule, you can say. For example, carbohydrate, protein and fat, and then we have different kind of food that contain the carbohydrate, protein and fat. For example, rice, potato, they have carbohydrate in there, fish, meat, proteins in there, and oil and butter have fat in there. And then if we eat this kind of food, we can get an idea how much calorie we are or how much energy we are getting in our body after metabolism, right? So if we eat a carbohydrate, it gives you a 4 calorie of energy for every 1 gram of the food sample that contain carbohydrate that you are eating it. Similarly, for protein, if you eat 1 gram of, let's say, fish, you are getting 4 calorie of energy from that every gram of fish. Same thing for fat. If you getting a 1 gram of oil or 1 gram of butter, you're getting 9 calories of energy for every 1 gram of the fat that you are eating. So that means fat gives you more energy compared to carbohydrate and protein. So this is how we can calculate how much energy or how much food sample we can take depending on how much calorie count we need for that particular day. Let's try to figure it out how we can use this information to calculate how much total calories that a particular food sample has, right? Let's try to do this thing on the next slide. Let's try to calculate the total calorie content on this food sample, that is, you can see on the right hand side of the PowerPoint, right? So the label on this food sample says you have 1.5 grams of the fat, 30 grams of the carbohydrate, and then 5 grams of protein in there, right? And let's try to calculate how much total amount of calorie we can get if we eat everything in there, right? So I know if I have 1.5 grams of the fat, and then we know from the previous table, if you eat 1 gram of the fat, you get 9 calories. So I can make a 1 conversion factor from here, 9 calorie on the top for every 1 gram of the fat. Gram cancel, you get 13.5 calorie. Same thing for carbohydrate. For every 1 gram of carbohydrate that you eat, you get 4 calorie of energy. So if you eat 30 grams, 120 calorie total. Same thing for protein. If you eat 5 grams of protein, you're getting total of 20 calorie in there. So what's the total amount of calorie if we eat this food sample? 153.5 if you add everything, right? And if you can see on the label, it says the total calorie is 150. So it's the same thing that we calculated. So that means they're showing the right value, what is written on the sample, because we already calculated and it's come out to be exactly the same, around 153, right? So that this is how you can calculate how much calorie any food sample has by getting how much amount of, in grams, how much amount of different fat, carbohydrate and protein you have on that food sample. Let's try to do one more problem on the same calorie count of the food sample. How many calories are in a cup of a pasta containing 32 grams of carbohydrate, 5 grams of protein and 1 grams of the fat? And we already know the equivalency. So if we have 1 grams of fat, every 1 gram gives you 9, so 9 calorie. 32 grams of the carbohydrate, every 1 gram of a carbohydrate gives you 4 grams of 4 calories, so total is 120. Similarly for protein, 5 grams 20 calories, the total is 157. So if you round it out to the 10 places, come out to be around 160 calorie. So this is how you can calculate the calorie content of the food sample, in this case is a cup of pasta, right? So if you're eating a cup of pasta containing these different food sample, 32 grams, 5 grams protein, 1 grams of fat, that means you are adding or getting 160 calories as an energy. So now let's talk about how our body can normally get energy, right? So our body is constantly doing a chemical reaction, right? And then this chemical reaction is a sequence, right? It's not just one chemical reaction. So our body normally do a sequence of chemical reaction, which we normally call as a biochemical pathway. So what is biochemical pathway? Is a sequence of chemical reaction leading to a particular product. So let's take an example. Let's say this is one of the reaction. A goes to B. This is one chemical reaction in our body. So this product B is now as a reactant to make another product C, right? And then now if the product you're making is C now, then C can be used as a reactant and make another product called D. So in our body, the reaction is in a sequence manner. So the product of one of the reaction can be used as a reactant for the second reaction, right, to make a product C. And then this product C can be used as a reactant for another reaction in our body to convert that into a D, right? So this is a sequential chemical reaction, which we call as biochemical pathway. So there are two type of pathway that our body use. One is called catabolic pathway, one is called anabolic pathway. And let's try to compare between these two pathway, right, on the next slide. So now let's try to compare the catabolic and anabolic pathway in our body. So catabolic pathway is where you normally break down a bigger molecule into a smaller one. So that means convert larger molecule into a smaller one. So you're breaking the molecule. If you're breaking the molecule, that means you're releasing energy, right? And if you're releasing energy, that means that energy may be used by the body to do some other function, right? And that energy that is being released during this catabolic pathway is normally stored in the form of a special molecule we call as ATP. So ATP is a molecule that absorb the extra energy that is being released through this catabolic pathway, and this ATP now can be used by another chemical reaction in our body as a source of energy. So we can say this is a source of energy, because all the energy that is being released during the catabolic pathway is stored in this molecule called ATP. So now let's talk about the anabolic pathway. Anabolic pathway is a building of a large molecule from a smaller one, right? Whenever you have a smaller molecule, when you have to make a bigger molecule, means you are making a new bond to make a molecule bigger and bigger and bigger. So that means when you make a molecule, bigger molecule, you need energy, and this ATP that is being stored during a catabolic pathway is now being used in anabolic pathway, right, to make a new molecule, bigger molecule. For example, this ATP can also be used in anabolic pathway to make protein, lipid and DNA, which is a bigger molecule, right? And like I already told you, is use energy from the catabolism, right, in the form of ATP. So this is how these two are related. Let's try to see a pictorial diagram of this catabolic and anabolic pathway on the next slide. So now let's try to take an overview of the metabolism. So metabolism is a combination of two pathways, anabolic pathway and catabolic pathway, right? And let's see how they're connected. So whenever you have the catabolic pathway, if you eat protein, carbohydrate and fat, so that means the body need to break them apart, right? So if the body is breaking these three food sample into a smaller particle, that means the energy is being released within the body, and this energy that is being released during catabolic pathway is going to be used during anabolic pathway, because anabolic pathway you normally build up things like cell membrane, DNA, protein. So body need energy to make up these things up for our body or a cell. So to make a DNA, body need energy, and from where the energy the body is getting is by breaking down these food sample during a catabolic pathway. So they are interconnected. and this is we call as metabolism. Now let's try to do a problem based on the concept that we did for the catabolic and anabolic pathway. The part A says when you build a muscle protein from a smaller amino acid, because we know what is protein. Protein is a combination of smaller amino acid. So you are making something. So that means this is anabolic pathway. The second one is a bear burning fat during the hibernation. So if the bear is burning the fat, means bear needs energy, and then how is going to get energy? From burning the fat. So fat is converting into a smaller molecule. So in this process we're getting energy, right, to sustain the life during the hibernation. So this is catabolic pathway. So this is how you can apply the concept of anabolic and catabolic pathway to figure out which kind of reaction is going on at that particular time. Now let's get started with the second part of this PowerPoint, which is the rate of the chemical reaction. So in this part we're going to talk about how fast the reaction can go or how slow the reaction normally go, right? What are the factors that affect these kind of rate of the chemical reaction? How do we know whether the given chemical reaction is getting faster or slower, right? That's why we call as rate. So previously we just talked about the energy related to the chemical reaction. Now on this topic we're gonna talk about how fast the reaction normally goes, right? Whether reaction is faster or slower. And how would I know? You normally get the rate of a chemical reaction by measuring it, the disappearance of the reactant or by the appearance of the product. What does it mean? If you have A goes to B and you have to figure out the rate, how fast the reaction is going or how slower the reaction is going, you just measure it by the disappearance of the reactant, how fast the reactant is disappearing during the chemical reaction, right? If the reactant is disappearing faster, that means you are making more product faster. Or if you can measure the appearance of the product, if you can measure how much product you are getting every time, whether you are getting faster or slower, you can predict the reaction is going faster or slower. For example, there come couple of the chemical reaction in real world that you can apply to get the understanding of this rate of a chemical reaction. For example, the spoiling of the food is a slow process, because if you put some food outside, it might take some days or right, or at least a week before it can spoil, right? Or the other type of reaction that we can use is a fast reaction. The fast reaction is airbag reaction. For example, if there is a car crash, the airbags that we have in the car deployed faster, right, the time of the crash. So that reaction is very fast, right? So this is how you can measure whether the reaction is slower or faster. So now we're going to talk about a special term called activation energy, and we're going to learn what this means. But before we go to the activation energy, let's try to understand how the chemical reaction goes. Let's say you have A and B, two reactant, and when they react they form C as a product. But what need to be happen before it can convert, A and B can convert to a C? These two atoms has to combine together, must collide with each other, right? Without collision between A and B, this reaction cannot happen, right? So sometimes the molecule or the atom may be colliding with each other, but you never get any product. Why? Because you don't have enough energy after collision, right? So just remember, the atom, when they collide each other, must have a minimum amount of energy before these two atoms can combine with each other in a reaction and convert into a product. So this minimum amount of energy that must be attained by the reactant molecule for a chemical reaction to occur, we call as activation energy, right? So for example, let's say one more time, let's say if you have two atoms A and B, right? And they are moving, the atoms are moving, right? And then if they collide with each other, after collision, what's going to happen? Some energy is going to release, and then that energy release is, let's say, 3 joules. But for the chemical reaction to happen, we need at least 5 joules of energy. So that means this 3 joules of energy is lesser than 5 joules, that the atoms or the reaction won't happen, right? But if the same kind of atom, if they're coming out with a higher energy now, and when they collide, they release 6 joules of energy. So that means they already have the minimum amount of energy that these atoms needed to convert these A and B into a C, right? So this minimum energy of 5 joules we call as activation energy. So each atom, before they convert into a product after colliding with each other, have to have some minimum kind of energy, and this energy is activation energy. And then energy diagram also show activation energy at the highest point. So whenever we go to the next slide, we'll see how does the energy diagram normally tells you where the activation energy is, where is the minimum amount of energy is, right? So let's go to the next slide and try to understand what is activation energy using an energy diagram. So this is the energy diagram that we already discussed on the previous slides when we talk about the exothermic and endothermic reaction. And then we already know this is an exothermic and this is endothermic reaction. But on this slide, we're going to talk about what is activation energy. If you can see, this is an EA. So activation energy, we usually denote it with an symbol EA, right? And the activation energy is the energy difference between the reactant energy and the highest point in the graph. So this difference is your activation energy, right? Or you can also identify activation energy and treat this graph as an uphill. So how much energy that the reactant has or need to have before it can reach to the top of the hill of this energy diagram. So the energy required to reach on the top of the hill, because after it reaches the hill, it's automatically converted into a product. So the reaction has to have this minimum amount of energy so that it can go to the top of the hill, which we call as activation energy. So for an exothermic reaction, if you can see, the activation energy is the difference. Whereas for endothermic reaction, you have the reactant again, right? Let's move it a line and then pick the topmost line on the graph and see what's the difference. The top. So this is the activation energy for endothermic reaction. And if we compare the activation energy for exo and endothermic reaction, so from the graph we can say for an endothermic reaction, the activation energy is higher compared to an exothermic reaction where the activation energy is lower. That means you need more energy, or the reactant needs more energy in the form of activation energy before it can convert into a product, compared to an exothermic reaction where you need, or the reactant needs, less amount of energy before it can convert into a product, right? And again, you can also see how much energy you need to just go on to the top of the hill. You need more energy, right? Because the slope is higher for an endothermic reaction. So this is how you can predict whether the reaction is going higher, or the activation energy requirement is higher or lesser in endo and exothermic reaction. So now let's go to the next slide and we try to understand how does this activation energy affect the rate of a chemical reaction. So on this slide, we're going to learn about how the activation energy affect the rate of a reaction. How would it tell us whether the reaction is going faster or slower, right? So the rule says, or the concept is, larger the activation energy, slower the reaction, right? And then it's not related to the heat of a reaction. This is very important, right? So we're going to discuss about this thing more, but let's talk about this. Larger the activation energy, slower the reaction. How is it possible? So let's try to do this thing on the left side of the energy diagram. So this is an exothermic reaction. This diagram belongs to an exothermic, And if you can see, the difference between the reactant energy and the top of the hill is this EA, activation. So you need, and if we compare with another exothermic reaction, right, because the product is less, has lower energy compared to the reactant, because, and that's why both of them has exothermic reaction. So if you can see, the activation energy for the second reaction is this one. So as the graph is saying, this reaction is a slower reaction compared to the right hand side one, which is a fast reaction. And how would we know? By looking at the height of this activation energy. So you can say, bigger the hill in the graph on the left hand side. Let's start with the reactant. You need to go to the hill, and then you have lot of distance to cover, right, before you can go to the top of the hill on the left hand side, compared to the right hand side, where you have less amount of energy requirement before you can go to the top of the hill, right? So that means you need less energy for the right hand side reaction to get to the energy, and then once it can convert into a product, right? So remember this thing, if you have the bigger height of the activation energy compared to the second reaction, that means that reaction is slower. Larger activation energy, slower the reaction, right? Let's take one more example over here. If I have a graph, this is your reactant, and this is your product, right? And then second reaction is this is again your reactant, this is your product. So if you can see carefully, where's your activation energy from the top one? This is your activation energy, the difference between reactant and the top part. So you need more energy to go uphill and reach to the top, compared to the second reaction over here, where you need less energy to go to the top of the hill. So this reaction is faster compared to the top one, which is slower, right? So this is how you can do. And the second thing that you need to know from this energy diagram, and what is important, that the activation energy is not related to the heat of the reaction. If you compare both the graph again, these two graphs, if you see the delta H of the reaction, is there any difference between the delta H of the reaction, heat of a reaction, between the two, faster or slower reaction? No, because the delta H of the reaction doesn't depend upon how fast the reaction is going or how slow the reaction is going. It only depends on the difference between the energy of the reactant when they started and the energy of the product when they stop. And if you can see, for both the reaction, the energy of the reactant and product are same. It's just only the difference of how fast the reaction is going, how faster the product is being formed, or how slow is the reaction is being formed. It doesn't change the energy of the reactant and product. So that's why the delta H of the reaction also is not going to change. So that means the activation energies doesn't change the heat of the reaction. This is important. So make sure you understand this concept. Let's try to do this problem and try to understand the concept that we just learned on the previous slide of the energy diagram of activation energy. So it says you have to draw the energy diagram of two exothermic reaction. That means the product has lower energy compared to the reactant with a different EA. So one of the reaction maybe have higher EA value, activation energy, second is a lower value, but with the same delta H of the reaction. And then you have to include these labels, right? You have to label the axis, you have to label the reactant and product, tells which reaction is faster reaction, show the activation energy with an arrow, show the heat of reaction with an arrow. So let's try to solve this problem on the next slide. So if you can see over here, you already have the two diagram based on the question that they ask over here. So we have two reaction, one We already labeled the excess energy and the reaction in progress for both of them. We already labeled the reactant and product for both of them, and we already made two exothermic reaction. Why both of them are exothermic? Because the energy of the product is lower than the reactant in both of them, right? If we compare both the graph. Then the other one that we need to label is activation energy. If you can see, the activation energy of the first reaction is bigger compared to the second one, right? So if this activation energy of the second reaction is smaller, that means you need less energy to go to the uphill to the graph, right? You need very less amount. So that means the faster the reaction goes to the uphill of this hill, the top of this hill, the faster the reaction is. So that means this is a faster reaction, or this is a slower reaction, because you need more energy to go to the top of the hill, right? So this is how you can make a graph and label everything. And the last thing is delta H of the reaction. If you can see, the delta H of the reaction doesn't change because is the difference between the energy of the product. It doesn't depend how big is the activation energy, how small is the activation energy. So delta H of the reaction is same for both of them. And then what's the value? Less than 0, because this is an exothermic reaction. Now let's try to talk about the factors that might affect the rate of the reaction. What are the factors that can tell you whether the reaction is going to be faster or smaller, right? And we already know about this is the activation energy that normally tells you whether the reaction is going to be faster or smaller, because this is the minimum amount of energy that the reaction need before it convert into from reactant to a product side. So we can say if there is any factor that can affect the activation energy, that means it's also affecting the rate of the chemical reaction, right? So there are three factors that might affect the activation energy. One of them is concentration, temperature, which is a heat, and the third one is the presence of the catalyst. So we're going to talk about each of them separately and then try to understand how does this affect the activation energy of the chemical reaction. So let's start with the concentration first. So now let's talk about the first factor that might affect the rate of the reaction, whether the reaction is going to go faster or smaller. Is this the concentration? So how does the concentration of the molecule can affect the rate of the reaction? So how does the concentration affect? So if we know that before the chemical reaction goes from the reactant to the product side, the atoms of the molecule has to collide with each other. They has to come close to each other so that they can do a chemical reaction, right? So the requirement is more collision. So if you have more concentration of the same reactant or the atoms within a small amount of volume, that means you're making it. So if you increase the concentration, that means you're making it higher chance, or there's a higher chance of the atoms that they can collide with each other compared to the one that has less concentration, because the atoms doesn't have anywhere to go. They are more concentrated. So higher the concentration means more chances of colliding with each other. If they're colliding with each other, there's a more chance of making a new product, right? So that means if you increase the concentration, the rate of the reaction also increases, right? They're directly proportional. Concentration, rate of a reaction. And if you can see the graph on the right hand side, the y-axis says the rate of the concentration of the reactant and its time. So if you can see, the graph is more steeper when the concentration is higher, 100%. You need less amount of time, right? Compared to the one if you have less concentration, the graph is now less steep. You need more time to get the same number of product compared to one that we have more concentration of the reactant before. You need less time, right? So this is the concept. Now let's talk about the second factor, which is heat or a temperature. How does it affect the rate of the reaction? So what happened when we, let's say, what happened when we heat any container that has a molecule in there? So when you're heating the molecule, you are increasing the kinetic energy of the molecule, right? if you're increasing the kinetic energy of the molecule, now the molecule is moving way faster compared to when you have a lower temperature or less heat, right? So if you're increasing the temperature, the molecule is getting heat, and then they're converting that heat into a higher kinetic energy. They're moving faster. If they're moving faster, there's a high chance they're gonna collide with each other faster compared to one when they're moving slower, right? So that means heating the molecule, or by providing heat to the molecule, you are increasing the rate of the reaction. Why? Because you are increasing the chances of collision compared to when the molecule has less amount of energy, right? So it says greater kinetic energy leads to more collision, right? And by experimentally, it has been shown that every 10 degrees Celsius increase in temperature of the molecule, the reaction rate normally doubles, right? And the lower temperature means slower reaction, because atom doesn't have kinetic energy. They are moving slower, so they need more time before they can collide with each other, right, to travel the distance between them. So this is how the heat or the temperature might affect the rate of a chemical reaction. And the third factor that increase or the rate of chemical reaction is the catalyst. And what is catalyst? Catalyst is a substance that speed up the chemical reaction without getting consumed in it, right? So catalyst is any substance that can increase the rate of a reaction by lowering down the activation energy. So how does the catalyst increase the rate of reaction? By lowering down the activation energy. So this is the important function for catalyst, right? And it also provide alternate pathway between reactant and product. So reactant and product without catalyst goes from another pathway, but if we put a catalyst in there, they might use a different pathway to reach the product faster, or convert from reactant to product faster. The third one important thing is do not affect the heat of a reaction. Like we already know this thing, right? Because catalyst lowering down the activation energy is changing the activation energy, and we know activation energy doesn't change the delta H of the reaction from the previous slide. So that's why catalyst also doesn't affect the chemical reaction, the heat of a reaction, right? And catalyst, like I already told you, is not consumed during the reaction. So once the reaction is done, catalyst can be used again for another chemical reaction. It's not converting into a product or not getting consumed, right? So now we're gonna see one energy diagram where you have two reaction. One of them is without a catalyst and one of them is with a catalyst. So, and then we're gonna figure it out how the energy diagram looks based on the chemical reaction. So now let's compare the energy diagram of a two chemical reaction, where in one of the chemical reaction we use a catalyst, and the second one we haven't used the catalyst, right? So let's say this is your reactant, product, and you have two energy diagram, right? The one on the top and second one with a solid line, right? So this one, the top one is without catalyst, the bottom one is with catalyst, the blue one, the purple one, right? So what you're seeing over here, the reaction without a catalyst has higher activation energy compared to the catalyst that has smaller. So they're going through a different path compared to without catalyst, right? So the activation is lower, that means the reactant is converting into a product faster, so the rate of the reaction is faster compared to one that doesn't have any catalyst. And if you can see, delta H of the reaction is same for both of them, without catalyst and with catalyst, because the energy of the product and reactant are same. It's just about how fast the reaction, how fast you are making a product. That's the only thing that is getting changed with catalyst, right? So just remember this thing. If we get any graph with lower and higher activation energy, you can easily predict which one should be energy graph with a catalyst. And how would you know that? So though that energy diagram that has a smaller activation energy, that graph belongs to a catalyst. So now we're going to talk about the biological catalyst. So we all know what is catalyst. In the previous slide, catalysts are those substances that can increase the chemical reaction by decreasing the activation energy, right, without getting consumed during the chemical reaction. So in our body, in living organism, we also have a catalyst that normally perform many chemical reaction. We call those catalysts as enzyme, right? So enzymes are the biological catalyst that perform many chemical reaction or speed up the many biochemical reaction in our body. So let's talk about a little bit about enzyme. Enzymes are essential for life, like I told you, because enzymes are the biological catalysts and speed up the several chemical reaction or biochemical reaction in our body to sustain life, right? And why we need enzyme in our body? Because uncatalyzed and biochemical reaction are way too slow, and then they won't provide enough amount of energy to the body in a right time, right? Because if we won't have any enzyme in our body, the reaction will be slower, and then if our body required energy, they won't get the energy because the reaction is still going on that might provide the energy. So this is the importance of enzyme in our body, right, to speed up the chemical reaction so the requirement of the energy is fulfilled. And enzymes is made up of proteins mostly, and we're gonna learn more about enzyme when we go into the biochemistry part, right? And then if we miss some enzyme, if the body misses some enzyme that is crucial for some of the important chemical reaction that body need, that might lead to some disease condition or some condition, right? For example, one of the problem is lactose intolerance. That means the enzyme that convert lactose to a glucose and galactose is not present in the body of the person that has lactose intolerance in there. So what's the enzyme that doing this conversion? Lactase. So that means that person doesn't have a lactase enzyme, so it's take very long time, or they won't even digest or degrade this lactose in the body. So that's why enzymes are very important. Let's try to do some of the problem based on the concept that we just learned. So the problem says explain if the indicated change will increase or decrease the rate of the chemical reaction. If this is the chemical reaction going on, and if heat is added to this chemical reaction, or you can say the temperature increases, what's going to happen? So we just learned if we increase the temperature or if we heat the chemical reaction, that means the rate of the chemical reaction will increase, right? So that means in this case it will increase. The second reaction is the reaction going on. It says sodium iodide, which is a catalyst, is added to the reaction, and we know once we added the catalyst to the chemical reaction, it speed up the chemical reaction. So that means the rate of the reaction also increase. For this, rate of reaction will increase. So this is how you can apply the concept and then figure it out whether the rate of the reaction is going to increase or decrease depending on the factor which is provided you into the problem. So these are the solution of the problem that we already did on the previous slide. So for the answer for the problem number 1 is increases, right? Because energy increase the number of collision, so that's why it increases. And this is the solution for the part B, where we had a reaction, and then if we added the catalyst, it increased the rate of the chemical reaction because catalyst lower down the activation energy. This is how catalyst increase the rate of the reaction, and we already talked about this thing before. So make sure you remember all this concept. So this is the last topic for this PowerPoint of this chapter, which is called chemical equilibrium. So in this topic, we're gonna learn about what is this equilibrium related to the chemical equation. So let's go to the next slide and then try to understand what is this chemical equilibrium. So let's try to learn about the reversible reaction before we go to the equilibrium reaction. So till now we just learned about this thing. Let's assume we have a reactant A that goes to B. So till now we just learn about that whatever the reactant we started with is always converted into a product fully, right? If you started with 1 mole, after the reaction is done, you're gonna get 1 mole of the product and you will get 0 on this side, because everything that you had at the beginning is already converted into a product, right? So till now we just learn about this thing, but there are some kind of reaction that doesn't go to a complete reaction, like we did in this example A to B. So this reaction is a complete go to completion, means everything that you started with is already converted into B, but some reaction is not going, is normal, usually doesn't go to a completion, and we call those kind of reaction as reversible reaction. And what is reversible reaction? That means in reversible reactant, the reactant, for example in this reaction that we had on the PowerPoint, hydrogen gas react with iodine gas to make a product hydrogen iodide. So in this reaction, the reactant come close together, collide with each other, and then convert it into a product. But in reversible reaction, the product, you have 2 molecules of HI and HI. The product might interact with each other too and then convert into a reactant in a reversible reaction. So this is we call as a reversible reaction, where the reactant convert into a product, and after some time product by itself react with each other to convert back into a reactant, right? So the forward reaction convert reactant to product. Similarly, the reverse reaction convert product to a reactant, and then we call as a reversible reaction. So the previous slide we just learned about the reversible reaction. So we did the same example, H2 react with I2 goes to 2HI, and then what's the special thing about the reversible reaction? You will see a 2-sided arrow like this. So that means the reaction is going back and forth, right? Sometime you're gonna get product, after some time the product is going to react with each other to make a reactant, so you can get forward and reverse reaction. So when the rate of this chemical reaction that can go forward and reverse, so when the rate of these forward reaction equal to the rate of the reverse reaction, then we call that the chemical reaction are in equilibrium, right? So that means the concentration of the reactant and product are constant and the reaction has reached equilibrium, right? So make sure you remember, at equilibrium the concentration of the reactant or product is not gonna change, right? And then the rate is going to be equal. So whatever the number of products you're gonna form, the same number of product is gonna convert back into a reactant form. So the concentration won't change during equilibrium. This is the most important thing. Okay, so let's try to understand what's going on during this reaction from the starting to the ending. So the first hydrogen and iodine molecule combine to form hydrogen iodide, right, as a product, and then hydrogen iodide decompose to form hydrogen and iodine, right? So the reaction is keep going reverse and forward. As the reactant are consumed, rate of forward reaction decreases. So what does it mean? If we start with certain amount of the reactant, and during the reaction if the amount of the reactant is getting lesser and lesser, means more reactant are getting consumed to make a product, that means the rate of the forward reaction is also going to get decreased, because now you don't have enough concentration of the reactant, because most of them is already converted into a product. So as the product are produced, the rate of the reverse reaction is getting increases. So that means if you have lot of product being produced, now the product side concentration is higher, means there is a lot of collision between the product molecule. That means the reaction can go backward, reverse, right? And then after some time the rate of the forward reaction becomes equal to the rate of the reverse reaction, and that's how we reach the chemical equilibrium. And at this chemical equilibrium, the concentration won't change anymore. right? So concentration stop changing, but the reaction is still going back and forth. Reaction won't stop, only the change in the concentration won't happen anytime more. So this is called chemical equilibrium. So once the reaction is in equilibrium, let's say if you have A goes to B and this is in equilibrium, so back and forth arrow. So for some reaction, if that reaction is in equilibrium, sometimes the concentration of the product is higher compared to the concentration of the reactant. Even though the reactions are equilibrium, that means the reaction is favoring the product side compared to the reactant side, right? But for some other reaction, the concentration is vice versa. The concentration of the reactant may be higher compared to the concentration of the product. That means the reaction wants to favor the reactant compared to the product. That's why the reaction is going more toward the reactant compared to the product, and that's why the reactant has more concentration compared to the product concentration. So depending on in a chemical equation, if that one is in chemical equilibrium, so depending on which part of the reaction has high concentration, whether it's product or reactant, you can tell which part of the chemical reaction is more favored during that reaction, right? So this is how you can analyze the chemical reaction which is in equilibrium. So let's try to get that concept that we just did on the previous slide. Let's take an example. You have two reactions going on, A and B. In A, H2 react with I2 to give HI, and then the reactant and product are already shown you different color balls. Similarly, for the second reaction, N2 and O2 react to make 2NO, and you also have the different color balls over here, right, for the reactant and product. So if you can see, the reaction is going on in that space. So after the reaction is reached equilibrium, what you're seeing over here, you have more amount of product compared to the reactant, even though the reaction are in equilibrium. So that means that reaction, this one H2 plus Si2, favoring more product compared to the reactant. That's why you have more product in equilibrium compared to the reactant. Similarly, in the second reaction, you can see you have more amount of the reactant compared to only 1 or 2 molecule of the product. So that means for this reaction that is in equilibrium, because you have back and forth arrow, this reaction is favoring more reactant compared to the product, because the concentration of the reactant is more compared to the product in this equilibrium reaction. So this is how you can analyze whether the reaction is going more toward the reactant or more toward the product. So now we're gonna start with a special term called equilibrium constant, and then we're gonna learn what does it mean and how we can use this equilibrium constant to figure it out whether the reaction is more favoring more toward the reactant side or more toward the product side. So for any reaction which is an equilibrium, let's say A goes to B, and this reaction is an equilibrium, and how would I know that this equilibrium reaction is favoring more the product side or the reactant side? So we're gonna use a constant called equilibrium constant, which is always product side over reactant, and then you have to put square boxes around product and reactant. And this, what's this square mean? This we call as, whenever you see these square boxes, that means we are talking about the concentration. So that means equilibrium constant is equal to the ratio of the product concentration or the concentration of the reactant, right? Product over reactant. So we can say B, because our product is B and reactant is what? A. So we have two ratio. If we know the amount of the concentration of both product and reactant at equilibrium, if we divide these two things, you're gonna get some number for KQ, right? If that number come out to be more than 1, that means products are favored. Why? If the top number is bigger, numerator number is bigger, that's how you can get KQ more than 1, right? So that means you have more concentration of B. And how you can get more concentration of B? when you have more product, that means product side is more favor. If KQ is less than 1, that means now you have reactant concentration more compared to the product one. That's why you get the value less than 1 for KQ when you have the bottom part or the denominator part is bigger. That means reactant is favored. You have high amount of reactant in the reaction mixture compared to the product. So how are you gonna get more reactant? When the reaction is favoring the reactant side. So by looking at the number of KQ, whether it's more than 1 or less than 1, you can easily figure it out. The reaction is favoring product or reactant side. And then we're gonna apply this concept later on, but make sure you know this concept. So now let's talk about a little bit more about the KQ equilibrium constant that we learned on the previous slide. We just learned if KQ is more than 1, that means reaction is going towards the product side. If the equilibrium constant is less than 1, that means reaction is going more towards the reactant side. But what's gonna happen if KQ is equal to 1, exactly 1? That means the reaction is in equilibrium. You can say just equilibrium. That means the reaction, the concentration of the product and reactant side are equal, right? So the reaction is not going or is not favoring any one side particularly, like it's not favoring product or reactant. They have equal favoring on both sides, reactant as well as product. So this is important too, right? So make sure you know whether it's more than 1, less than 1, or exactly equal to 1. Okay. So now we're gonna understand what's gonna happen if any reaction is at equilibrium and something changes. For example, let's say if this reaction A goes to B, this reaction is an equilibrium, right? And if I change something, let's say if I increase the temperature of this chemical reaction, if I decrease the concentration of this chemical reaction, which is an equilibrium, what's going to happen to this equilibrium now? So Le Chatelier principle is the principle that normally tells about what's going to happen if any chemical equation which is in equilibrium, and if you change something, any factor, then what's going to happen to the chemical equation. So this is normally given out by a rule called Le Chatelier principle. So according to this principle, it says a reaction at equilibrium responds to a disturbance to counteract it and reach a new equilibrium. Or we can say in the other way that if a chemical system is at equilibrium, is disturbed or stressed, then the system will react in the direction that counteract that disturbance or relieve the stress, right? So we're gonna learn, or we're gonna do some example to understand what is Le Chatelier principle and what does it says. So what are the common disturbance or the stress that you can give to the chemical reaction which is an equilibrium? First, you can add or remove either reactant or product. You can add more reactant, more product from the outside, or that means you are putting some extra concentration which was not part when the reaction was at equilibrium. The second one is you can add or remove the heat, or you can add, increase or decrease the temperature of the chemical reaction. So there are two ways you can disturb the chemical reaction which is an equilibrium, and according to Le Chatelier principle, we'll see how does the chemical reaction react to these changes, right? So let's go to the next slide and then try to understand this Le Chatelier principle. So the first disturbance that we can add to the chemical reaction which is at equilibrium is by either adding or removing a reactant at equilibrium, right? Let's do both of them. So if you can see the chemical reaction A and B on the bottom of the slide, let's say if this is the reaction going on, H2 react with I2 gives you HI, and then this reaction is in equilibrium. If we add more hydrogen gas from outside to this reaction which is already in equilibrium, what's going to happen? Now you disturb the chemical reaction by putting more hydrogen gas to this chemical reaction from outside. So now the reaction will see this addition of hydrogen gas or addition of more reactant as a disturbance, and then it tells the chemical reaction, okay, so we have to balance this hydrogen gas concentration again in a chemical reaction. So the reaction will go more toward the product side because the chemical reaction needs to consume an extra hydrogen that we added to the chemical reaction, right, to go into the same concentration that we have before we added any reactant in there. So that means the reaction will go away from the disturbance to neutralize the disturbance. So that means it's going from left to right, making more product. Now let's try to do the second type of disturbance where we remove some of the reactant, in this case hydrogen gas. What's going to happen if I remove the hydrogen gas from the chemical reaction which is in equilibrium? So that means now the chemical reaction will see, okay, now I don't have enough hydrogen gas to be remain in the chemical equation because somebody took it out, the hydrogen gas. Then the reaction will go backward to counteract this disturbance to make more and more hydrogen gas, because now the chemical reaction need to make more hydrogen gas to balance the amount that is already been taken out, right? So then now the reaction is favoring more reactant side, right, to counteract that disturbance. So this is how the addition or removal of the reactant work in a chemical reaction. Now let's try to do exactly the same but on the product side on the next slide. So now we have the same type of equation again and A and B, but what's we doing over here? We are adding or removing the product, right? So in the equation A, reaction A, we are adding more hydrogen iodide to the reaction mixture which is an equilibrium. So what's gonna happen if I add more from outside? Now that we are disturbing the chemical equilibrium, and if we are disturbing it, now the reaction have more amount of product that it was before when it was in equilibrium. So the reaction will try to consume an extra product by converting product into a reactant side, so that it will have the same amount after some time, right? So now the reaction will go backward to make more reactant, right? Let's go to the second scenario where you're removing the product. If you're removing the product, you're decreasing the concentration of this product in a chemical equilibrium. So now the reaction will try to counterbalance this effect of removing the product by making more product, right? So now the reaction will go more toward the product side, right, to counteract this removal of HI or to make more product, right? So this is how you can determine whether the reaction is going toward the product or reactant side, depending on whether you are add or remove the reactant or adding or removing the product side, right? Now let's try to do the second disturbance that might affect the chemical equilibrium, and then we have to apply the Le Chatelier principle to figure it out whether the reaction is going backward or forward, right? So the second disturbance is removal or addition of heat, or by increasing the temperature of the chemical reaction or decreasing it, right? Because heat is what? Temperature. So there are two types of reaction that we know of. One of them is exothermic reaction, another one is endothermic reaction, right? So in exothermic reaction, heat is in the product side because the heat energy is released into the environment, is product side. For endothermic, you are providing heat to the reactant side. So remember this thing. This will help you to understand or figure it out whether the reaction is going toward the product or reactant side when you add or remove the temperature. Let's try to do one of the scenario where you add or remove heat for an exothermic reaction. what's gonna happen. So there are two scenarios, A and B. For exothermic reaction in A, when we add heat to the chemical reaction, means when we increase the temperature of the chemical reaction on the product side. So now, because this is an exothermic reaction, that means you already have heat on the product side. Now if you add more heat toward the product side, that means the reaction will think, okay, we already have more heat, why would we need to provide or release more heat to the environment? So the reaction will go backward toward the reactant side, because whatever the heat that this chemical reaction needed, you are providing from outside, right? So reaction doesn't have to go toward the product side to release more and more heat, right? Let's go to the second scenario for exothermic reaction. If you remove the heat that is producing from the chemical reaction, now you took out the heat from the chemical reaction. Now the reaction will think, okay, I don't have enough heat, or we are not providing enough heat to the reaction, so let's move to the product side and make more and more heat, right? So that means the reaction will go towards the product side. To counterbalance this removal of heat, they have to make more heat, right? And because the reaction is exothermic, whenever the reaction goes toward the product side, it will release heat. So that's why it basically favor the product side. And how would you know? By looking at the arrow. This arrow is bigger toward the product side, means the reaction is still in equilibrium but favoring more toward the product side. Same thing on the first scenario over here. The arrow is bigger on the reactant side, that means reactant side is favored. So this is how you normally do it. Let's do the second scenario where you add or remove heat for an endothermic reaction. Let's go to the other slide. So in this scenario, we are adding or removing the heat for an endothermic reaction, and we know for endothermic reaction we already have the heat on the reactant side, right? So let's take a first scenario where we add heat more towards the reactant side, right? So we already providing a heat on the reactant side. Now if we add more heat, that means you have extra heat on the reactant side. Now the reaction will think, okay, I have more heat that we needed, we have to go to the product side to remove that extra heat. So that's why you will see product is favored for an endothermic reaction when you add a heat. But when you remove heat, then the reaction will think, I don't have enough heat to convert into a product, we need more heat, so let's move the reaction backward to make more heat, right? So that's why the reaction is favoring the reactant side when you remove a heat for an endothermic reaction. So this is how you can analyze which way the reaction is going for an endothermic and exothermic reaction, depending on whether you're adding or removing the heat from the reaction that is in equilibrium. So now let's try to do one problem based on the concept of the Le Chatelier principle that we just learned, and then apply the same concept for this problem. So the problem is saying, if this is the chemical reaction that's going on, carbonic acid decompose into carbon dioxide and water, would an additional carbon dioxide in the blood cause a shift to the left or to the right? So if I add more carbon dioxide, where would the reaction will go? Towards the product side, toward the reaction side. The second problem is asking, carbon dioxide is removed from the lungs by exhaling it. If you're removing the carbon dioxide by exhaling the carbon dioxide from the lungs, would its removal cause a shift to the left or right, right? So we need to explain it. So let's go to the next slide and try to understand how you can solve this problem based on Le Chatelier principle. So the first problem says, if you add more carbon dioxide, where would the reaction will go? So carbon dioxide is in the product. If you add more carbon dioxide in there, that means you are increasing the carbon dioxide concentration on the product side. So the reaction which is in equilibrium try to maintain the concentration by converting the extra carbon dioxide to a carbonic acid. So that means the reaction will go more towards the reactant side or more toward the left side, according to Le Chatelier principle, because it has to counteract the disturbance that you provided it, right? The second part of the problem says, if you remove carbon dioxide, so again carbon dioxide is on the product side, if you remove that carbon dioxide from the product, that means you are decreasing the concentration of the carbon dioxide in the product. So that means the reaction will say, okay, we don't have enough carbon dioxide now on the product side, let's make more. So the reaction will shift to the right or towards the product side more, right, to counteract the lesser amount of carbon dioxide, right, because we already took carbon dioxide from the product side. So this is how we can apply the Le Chatelier principle to solve and then to figure it out where the reaction is going, whether in the reactant and product side. And yeah, so make sure you know this concept too again. And I think that should be it from this chapter, and then I'll see you in the next chapter or in the next video. Bye.